Okay, so the title of my talk today is Programming Quantum Computers Through Quantum Signal Processing. So a lot of you might be more familiar with classical signal processing. And by that, that is illustrated by this diagram. For example, we have an analog system that produce a signal such as a classical mechanical wave. And that signal is received by some electronic circuit to convert it into electronic signals. And then in turn to be able to transmit much farther distance, such as through our radio wave or microwave wavelengths. And that's then received and convert back to the signal that human ear can listen. So this type of process we call signal processing derived really way back in 17th century based on numerical methods. And so the underlying math is extremely old. However, this method the signal processing as a field did not flourish until after integrated circuit have gave birth to a lot of technologies that need signal processing specific processors, such as our cell phone, a radio, or even our laptop. And so this type of process, in essence, is trying to process signal that look almost random, for example, on the left, into something extremely meaningful in a very efficient manner. And today I want to kind of convince you that we can treat the process of programming quantum computer as also signal processing procedure. So I will start with a simple example in how we program quantum computer. So the first step is to identify a problem that you like to solve. For example, here I show you a problem of max cut on a 3 regular graph. 3 regular meaning each vertex has only connects to 3 other neighbors. And the task is to find a cut across this graph to meet as many edges as possible. So if you cut the maximum amount of edges, then you solve the problem. So the second step is we have to encode this problem into something that very friendly for quantum computer. More particularly, we want to encode the solution into a quantum state that we can prepare with a universal quantum computer. And luckily, there's a formulation called Ising formulation to solve a lot of graphical problems, including the very hard NP problem. So the idea is to treat each vertex on a graph as a spin, a classical spin that can take 0 or 1, and connection as the coupling between the spin. So then the ground state of a well-conceived Ising Hamiltonian can be correspond to solution to a graphical problem. So this mapping is already discovered, so we don't have to reinvent it, and we just use this method to map this graph onto Ising Hamiltonian. And then the third step is to actually come up with a circuit that prepare the ground state of that Hamiltonian. And one of the easiest way to do that on a near-term quantum computer is through so-called quantum approximate optimization algorithm. The idea is very simple, which is I just keep repeating this type of unit operation that consists of 2 steps. The first step is essentially doing some rotation around the quantum state based on how close the state, assign a phase that tell you how far you are from the state you would like to prepare. And then the second step is to just perform a general scrambling rotation implemented on each qubit. This is similar to, in essence, to a Groover search algorithm. And don't worry about Groover if you haven't learned about Groover search, but this is just one example of preparing a ground state of the type of Hamiltonian I showed in the previous slides. But then we also have to map this into a hardware grid, because what I showed you here is a logical circuit, right, on an idealized qubit. But in reality, qubits are not, for example, on a line. They literally lay on some 2D architecture. For example, what I showed you here is architecture we had at Google, where qubits, each qubit have 4 neighbors, so they live on a grid. But some qubits on the boundary only have 1 or 2 neighbors. So we have to accommodate this type of hardware constraint. Moreover, we have to be able to realize every step of this quantum circuit. For example, at the very beginning, we need to initialize the qubit in a specific state. Here I showed you in a superposition state. And the way we do it is actually to send an analog control signal into the superconducting circuit through coupling through many layer of dilution refrigerator, where I show you here with an analog signal form. And so similarly, we need to control the quantum gate also through a different shape or frequency of the analog signal. And last step, we also need to measure the qubit by moving the qubit frequency to the readout resonator in order to perform the measurement. And that movement is also introduced by another analog signal. So in essence, all we are doing is sending different type of analog control signals into the quantum computer and read out the measured control signals. So if you think about in the framework of signal processing, the input signal will be the signal that we use to control our quantum computer. And the output signal will be the measurement result that tell us about a certain solution to our target problem. But so far, what I have given this paradigm I have given you is still a classical signal processing. But it is very useful in giving us a new perspective of how we control our quantum computer. But to make it even more powerful, we have to make it quantum mechanical. So now I will introduce you what we call quantum signal processing. And I will start from a single qubit case. So if you have a single qubit in quantum mechanical models, it's represented by 1 point in a 3-dimensional sphere. We call it block sphere. For example, in the North Pole and South Pole represent 0 and 1 state, which is like a classical bit. However, quantum state allow you to have superposition of 0 and 1. Moreover, the amplitude in front of 0 and 1 can be complex. So that gave us 2 plus 2, but with a restriction that the probability of the 0 and 1 sum to 1. So you reduce 1 degree of freedom, so that you end up with a degree 3 of a spherical representation. So if I give you, for example, equal superposition state 0 plus 1, we can represent it by 1 point on this equator. So that's a description of the state. But once we have the state, we can think about what we can do to this single qubit. One of the description of the type of operation we can do is to let this state vector rotate around certain axis. And what I show you here is a specific axis which lay on the xy plane. So I want rotate on any vector around an axis defined by the angle between x and y for a rotation of theta angle. So then this is one of the simplest operation you can do to one single qubit. So For those who are not very familiar with linear algebra or quantum mechanics, I'll define it here a little bit more clearly. So the x and y are so-called Pauli matrices, together with a third one, z. They consist of a complete orthogonal basis to represent any 2 by 2 unitary matrix. And the rotation of a qubit mathematically is represented by multiplying a 2 by 2 unitary matrix onto the quantum state vector, which is a 1 by 2 vector, basic two numbers in front that represent amplitude of 0 and 1. So therefore, a rotation can always be represented by this type of matrix exponentiation of Pauli matrices. So that's how we represent this rotation. But if you're not comfortable with this type of linear algebra, you can just remember these two parameters. Theta is a rotation angle, phi define the axis of the rotation. And in reality, this type of rotation is again controlled by the analog control waveform. This is just an example of what that could look like. And so now I will define what a quantum signal processing could be. So now my input signal is no longer a classical signal. It's this unitary operation, this quantum rotation. I will treat that as a signal. But whenever we talk about signal, we're really talking about certain quantity that vary as a function of a variable. So here you can think of this varying variable as theta. Then the quantity of this signal is a unitary that change as a function of the input variable theta. So that's my input signal. Of course, it's a little bit more abstract, harder to visualize than a scalar input, right? Then you will have this type of line as a function of time. Then the time is a variable of your input. But so let's just bear in mind that my input signal now is a quantum rotation. And then the output signal here, I will define as the measurement probability of state transition from a ground state 0 after applying the input signal rotations and then transition to state 1. The probability of a bit flip after the application of input signal. So I'll be a little bit more specific. So for example, this is one type of output signal transformation with only one repetition. So now if I start from the ground state and I apply this type of rotation once, and then I measure the qubit, see what's the probability of this qubit end up in excited state. And the probability will look like a sine function. This is very straightforward because if you look at the unitary matrix of this rotation, we're really just probing one of the 4 elements of this unitary matrix, which is the sine function of theta. Great. However, if I'm allowed to do more transformation by adding more rotations, they are the same in regard to the rotation angle theta. However, they can differ in the axis of the rotation phi. For example, here I show you have phi equal to 0, 1.5, and another 0. Then the output probability, which is the y-axis of transition from 0 to 1, as you vary the theta angle, will look like a wavy flat top. So then we can continue to increase the number of pulses, a number of phi angles in the input. So this is a plot where if you have 5 consecutive pulses of 0, 1.5, 0, and 1.5, then you have almost a perfect flat top, almost like a smooth trapezoid. So in fact, if you give me any degree n polynomial function of theta, so here this is a cosine function of theta. But if you want any degree n polynomial of the trigonometric function of theta, we can always realize that with n different pulses of the theta and find the associated phi angles to realize that. So in that sense, this type of quantum signal transformation is universal for realizing a bounded function as a function of theta. So this is a result first discussed in this paper in a very important, initially it was introduced to design both quantum gate and to realize mitigation for qubit control. But later on, people realized this is much more useful than what it was originally conceived. For example, we can generalize this type of signal processing into the multi-qubit case. So to see how that generalization is done, we can first look at a single qubit case. So we are probing the transition probability here, 0 to 1, is basically probing this element and this element of a 2x2 unitary. And if we want a polynomial function p, an arbitrary polynomial function p of cosine theta, we can just solve some transcendental equation to find out what is the value of phi. So this is a single qubit signal processing. And if we want to generalize it to multi-qubit case, the only difference is we replace theta, which is just a scalar, with a matrix, a Hermitian matrix H, Hermitian and unitary. And then the polynomial will be over the matrix of the function we want to perform the universal transformation on. And you might ask, what is the usefulness to perform, universal transformation on matrices? So for that, we will quote Richard Feynman. He said once, nature isn't classical, and if you want to make a simulation of the nature, you better make it quantum mechanical. So in fact, this polynomial function p could be an exponential function of a Hermitian matrix. So those of you who have already taken quantum mechanics will realize that this indeed is a unitary evolution under the Hamiltonian H given by the Schrödinger equation. So what is the useful of realizing an evolution of a given Hamiltonian? It is if we set this Hamiltonian as a Hamiltonian that we care about in a realistic system, for example, an electronic molecular Hamiltonian, then we are really simulating the evolution of that given realistic system. And we know that in generic case, a classical computer will take exponential in the size of the system runtime. But by definition here, we only need polynomial in the system size runtime. So that gives us an exponential advantage for our quantum computer. But the application of that is much wider than that, because a very important algorithm in quantum mechanical computer design is phase estimation, where the subroutine of the quantum phase estimation require us to do exponentiation of a Hamiltonian. And that will also help us solve linear algebra exponentially faster than a classical computer. And similarly, we can use adiabatic algorithm to adiabatically change a system from one state to the other. And that also require us to be able to evolve the system under this exponential function. And that allows us to also solve many NP problems in potentially much faster than classical computer. However, despite the promise, we still are very far from making a practical use of this algorithm. For example, this quantum signal processing based algorithm so far is the most efficient simulation algorithm that we know in regard to its dependency on the sparsity of the Hamiltonian H. And the sparsity means the minimum number of non-zero elements per row for this Hermitian matrix, and the accuracy. It has the best scaling as a function of the accuracy for the runtime. The reason is, in order to use this algorithm to solve a practically useful problem, we have to achieve so-called chemical accuracy. And the chemical accuracy can be defined as the accuracy it needs to be able to predict the chemical reaction rate at the room temperature. And that's the situation where we care about, for example, in designing drugs and designing battery. And so to do that, we basically require the simulation itself to be of 10 to the minus 10 in the error rate. However, currently our quantum computer operate at error rate 10 to the minus 3. So there's a giant gap between the requirement to run this algorithm to perform this exponentially faster simulation versus the available device that we have. So then the question is, can we make quantum signal processing useful before we build a large-scale error-corrected quantum computer? And this leads to my last part of my talk. I want to show you that, in fact, we can use quantum signal processing towards our effort to build a fault-tolerant quantum computer. And I will talk to you about the first use case in practice of a quantum signal processing. And if you're interested in this work, please check out this paper, this preprint. Okay, so what do I mean by being useful? So for now, our quantum computer is not super useful in regard to using quantum signal processing or any algorithm at all to simulate a useful quantum system. So to get there, we need to rely on the so-called fault tolerance. And the fault tolerance of a quantum computer can be really encapsulated in this famous threshold theorem. The theorem states that a quantum computer can only reduce error as you increase system size if the initial error of the system is below a threshold. If you're above that threshold, the bigger the quantum computer is, the more error you will have. So it won't help you by scaling the quantum computer up in size. So the threshold that we are currently eyeing at for using, for example, surface code is 10 to the minus 4. And so this means that we have to be able to learn the non-ideality of our system with the accuracy that is around or below the 10 to the minus 4. And in reality, a lot of things can go wrong. So here I will show you the type of system Google have, where we have qubit that's coupled through another third qubit. So each circle I showed here is one qubit. You can think of it as almost like a harmonic oscillator, right? You have a capacitor and inductor. They're connected in a loop. So when you send in some current or voltage change, into the loop, you'll have some type of oscillation, and that oscillation can be used as a quanta of energy to represent qubit. The only difference is the inductor we're using here is a nonlinear inductor, which change as a nonlinear function of the voltage induced change as a nonlinear function of the current. And this is realized by this very famous Joseph junction, which consists of a superconducting material separated by an insulating island. And you have two copies consisting of a so-called squid. So you basically just insert another loop that looks like a third qubit to introduce a quantum gate. So you may think, oh wow, this looks extremely sophisticated. And in fact, it is pretty sophisticated in regard to its dynamics can be very complex. But still, the very advanced engineering allow us to realize the two qubit gate. For example, I represent here, I show you the full unitary matrix on the 2x2 unitary, which is on the 4x4 unitary on 2 qubits. We can still realize this unitary extremely accurately. There are still some non-idealities. For example, this is the actual unitary we can realize in practice. So you can see a lot of places they are perfectly zero, and this is because of the nice symmetry of our system, which conserve the total excitation. Because the ordering here, I use the first row to represent no excitation, the second, third row to represent a single excitation, either in the first qubit or a second qubit, and the last row is two excitation in both qubits. So it's already pretty nice that we don't have unwanted coupling between the quadrant that have different number of excitations, but still we have these unwanted phase theta that introduce unwanted swap between 1, 0 and 0, 1. So when we want to really reach the threshold of computation, we have to be able to learn the quantum gate parameter theta phi to the accuracy that near the threshold of the fault tolerance. And in order to do that, we define this problem of calibrating F-sim gate, which is if I give you the access to apply this type of non-ideal two-qubit gate, an arbitrary single qubit quantum operation together with projective measurement, the problem is to infer the underlying angle theta and phi of this imperfect quantum gate. And we want to reach the accuracy around or below the threshold of a fault-tolerant quantum computation. And the prior art to do this is based on a Heisenberg limited amplification. So the rough idea is if I repeat a quantum operation k time, then the parameter of that operation, for example, theta, will be amplified by a factor of k in the measurement outcome. And this is great because this amplification gives us a quadratic improvement for the variance of the estimator, which is much faster than linear reduction of the classical sampling error. But we will not focus on the Heisenberg limit here, and don't worry if you are not familiar with this scaling. But the main limitation of this prior art is that as we repeat this function, this non-ideal operation k time, the sum of the parameters of that operation can drift over each iteration. The consequence of that is we will no longer be able to achieve this type of quantum amplification. And for example, I show you here the standard deviation we measure in practice in its empirical distribution. That it dropped, it's definitely have a huge amount of them, is below 10 to the minus 4. Excuse me. So we want to come up with an algorithm that can achieve the extremely accurate learning that give us assurance on fault tolerance while tolerating this type of drift in the parameter of the quantum gate. And to do that, we really have to look a little bit harder on the unitary that we want to learn, this 2-qubit unitary. If we look at the unitary, we realize that the part that's inside of the 1001 subspace actually look very similar to the single qubit quantum signal processing unitary I showed you earlier. And so that means if we are able to limit the quantum dynamics within the single excitation subspace, we should be able to directly leverage quantum signal processing to design our circuit. And in fact, we are able to do that if we initialize our state in Bell state. So I define Bell state here as a superposition of 0, 1, and 1, 0. So I use 0L with the subscript 0L to represent 0, 1, and 1L as 1, 0. Then if I prepare my initial state in a Bell state, the dynamics of the gate is only described by this 2x2 unitary due to the particle conservation symmetry of our system. Then our algorithm will basically try to measure the probability of transition from this Bell state to 1, 0, and this Bell state to 1, 0. The difference between these two different initial states is really just in this tiny phase difference, I. And why do we have such a contrived state initialization? The reason is, so maybe I will skip the detail of the theorem, but I'll tell you that through signal processing, we realize that this specific arrangement of initial state allow us to separate this drift parameter completely into the phase of a Fourier component of our measurement, and the target parameter as the amplitude of the Fourier component. And so this is a flowchart of our this new metrology algorithm. We start with two different type of Bell state. We repeat this non-ideal gate d time. We measure the qubit and figure out the probability of measuring 0 and 1. And then we repeat the same thing as we sweep the parameter omega, which is a single qubit phase shift that is used as a knob in our quantum signal processing. And if I do that d2d minus 1 time, I can perform a Fourier transform if we treat this omega as a parameter of a frequency. And once we transform it, we can extract the theta as the amplitude of the Fourier space. And this is the result in the actual characterization of theta angle in our superconducting quantum computer. The x-axis is the variance of the theta with our method. But the y-axis is the method with the cross entropy benchmark, which is the prior art standard method. So you can see the prior art is spreading all over the place. And if you take a square root of that, it gives you roughly the accuracy. So it's vary from 10 to the minus 1 to 10 to the minus 3. But our method is very concentrated around 10 to the minus 8 to 10 to the minus 7, which give us the accuracy of around 10 to the minus 3 to 10 to the minus 4. So we basically increase the accuracy of the learning method by 1 magnitude, but at the same time, we were able to reduce the depth of the circuit by around 1 magnitude. So with quantum signal processing, we're able to have a more efficient and accurate learning algorithm. So maybe I will just quickly jump to the outlook of quantum signal processing. So one thing that classical signal processing, such as our noise canceling headphone using this type of circuit can be done, has not been done in quantum signal processing, which require real-time feedback, but also at the same time offer us an innate error correction mechanism. Without that, we might really have to wait for millions of physical qubits to arrive, which we don't know when that will happen. Another thing is if we generalize quantum signal processing beyond the gate error model and the gate model. So the type of circuit that we currently use to perform quantum singular value transformation, which is a more advanced version of quantum signal processing, is described by this type of blocks of gates and multi-qubit operations. Can we generalize that to accommodate analog nature of quantum control or other type of optimization present in our gate design and the quantum computer design, such as the discrete optimization for the circuit compilation or the architecture optimization. So that's the outlook, and summarize my talk, and thank you very much. And if you have any question, please send the question over email. And also I will be studying at University of Maryland, College Park in computer science department in the coming August. So I'll be recruiting grad student and postdoc.
That's great, Murphy. Really amazing talk. I come from a background in control systems, so a lot of this sounds familiar, and it's exciting to see how signal processing, there's a lot of stuff that we have, like that we already know from the classical world and from different fields that can come into play if you combine them with quantum computing, right?
Yes.
You had incredible results, by the way, and we have a ton of people
Thank
asking
you.
questions in the chat. But because I'm hosting today, I'm lucky and I get to ask you some questions. First, a little bit about your background. I'd like to know, how was your path into quantum computing?
Yeah, thanks for the question. So my path is a little bit a detour because when I was in undergrad, I'm actually into cosmology and high energy physics. But I did love linear algebra, and I remember back then the professor of that class told me, "Oh, linear algebra is very useful for physics," and everyone is not very convinced. And when they asked why, he said because there's this new emerging field called quantum computing. All they need is linear algebra. But back then I didn't pay much attention until I was interested in condensed matter physics. But then I took the class by Isaac Chong, who is also the author of one of the first quantum computing textbook. And I was really mesmerized by the simplicity of quantum computing, but also the striking result, right? Like Shor's algorithm is so simple, but somehow it can solve such a hard problem. And that really gave me a type of strike of, oh, wow, there's so many things, but it's such a young field compared to condensed matter physics, which is almost 200 years old. And quantum computing science is less than 50 years old. And so I was drawn to that through this type of taking the class and talking to Ike, and who eventually became my advisor. And then I had the honor to also work during my PhD, work with Google team. We applied for funding from Google, and that's how I also ended up in Google. So yeah, I would say it's a combination of exposure, like the fact MIT have such an amazing quantum computing classes, and the mentorship that I was able to meet people, so many great mentors in quantum computing.
Yeah, mentors can really make a difference.
Yeah.
You have someone who tells you, yeah, quantum computing is great, and then you actually start looking at the math behind it, and it's beautiful. So you get mesmerized and end up dedicating your life to that, right?
Yes.
um, I want to ask you also about your work at Google. Do you have any interesting anecdotes about working at Google Quantum AI?
um, I guess there's a lot of anecdotes, but I don't know whether I can share with you. But I think one interesting thing is like how much collaborations between Google and academia. For example, Alexei Kitav, the Kitav suffix code Kitav is now also uh, you know part-time in Google, and we always see him randomly in the meetings, and it's really nice to be able to uh, talk to some of the founding uh, people of this whole field. um, but I guess it's just a very like welcoming and open environment where I don't feel like being confined, right, to any specific group of people, but we're working with academia and other industry partner. Um, but funny, what type of funny are you expecting?
I just wanted to get an insight of like the people behind the science, right? QHack
Yeah.
is a little bit different. It's not just about listening and hearing and learning about the science, but also the people behind it. So that was
Yeah, people here are all different type. They're all interesting from different countries, uh, from across the world, and yeah, it's very hard to really pin down on one specific event. But in general, I'm very impressed by the diverse background, both culture and educational background. Right, people come from more traditional side of Google, or very traditional side of physics, like people who have come from NASA working on very hardcore classical control problem or physics problem, um, uh, and they join us, or people who are neuroscientists, like Harmon Navin, our group leader. He worked on neuroscience before working on quantum. So uh, I would say it's a very, very, very different depending on who you talk to, but it's extremely invigorating.
Yeah, absolutely. I couldn't agree more. Had a similar experience when I joined Xanadu, and one of my first meetings, the first day, Maria Scholt was in that meeting, and she is a super role model for a lot of people in the world, especially if you come into quantum machine learning, right? You hear about her,
Yeah,
and I had a similar experience. Like, oh my god, I'm in a Google Meet with Maria Scholt. Wow, that feels
yeah.
exciting.
We
Uh,
actually invited Maria over. Yeah, we actually invited her to Google a couple times too. It was amazing.
Yeah. And I guess people feel like that about you too, as well. You being here and everybody from all around the world right now in the audience being able to enjoy your talk and learn about this like very advanced topic that usually if we didn't have a virtual event, most people wouldn't be able to access this content, right? So um,
Right.
I feel very fortunate that we have these events so that everybody can get to enjoy them. And they can also
That's
ask
right.
questions in the chat, and we have a ton of them. So uh, let us take a look at some of the questions. Comp Fizmark asks, what is the difference between quantum signal processing and classical signal processing that encodes quantum information?
Yeah. Very good question. So the type of quantum signal processing we talked about here is pretty specific, right? Where the input, the type of transformation are allowed obey this very well-defined structure of application of a unitary followed by some phase shift, and then you can do them in any amount of time by changing this phase shift. So in that sense, it's very limited. It's a very, very narrow definition of a type of transformation. And the reason I call it quantum signal processing is because it was first invented in this paper by Guanghao Lo, Ted Yoder, and Isaac Chuang, and they use this terminology, right? But the true quantum signal processing should be much, much broader.
Yeah.
So the difference between, in that sense, classical processing of a quantum input is more broader, and it can, in theory, include what I call quantum signal processing as a subfield.
Okay. A great question. Great questions, everybody. We have a question from Tom Bum asking, for the single qubit case, I understand that you can approximate any function theta, but given any function theta, can you compose any function at all?
Given the function of theta, so there are two parameters, theta and phi, right? So you can perform any polynomial function of cosine theta if of degree n, if I have n different rotations to use. So I wonder, maybe I wanted some clarification on the problem. What does it mean to be any function at all?
Yeah, so Tom Bum, you can ask a clarification of your question. I would understand it more like, can you approximate any function with a single qubit? I don't know if that's possible.
Oh, I mean, if you, in theory, not any function, because it has to be bounded. It has to obey certain parity constraint, as shown in that reference if you look into it. So yeah, maybe the answer is no. If it's literally any function, then it's no.
Good to know the restrictions and where you need to pay attention, right?
Yes.
Okay, we have a question from Sai Ganesh Manda. What applications can this field see in the future? Will it lead to any groundbreaking realizations?
Yeah, I like this question. So I think the future, to me, in quantum signal processing is really to integrate error correction. So far, our quantum error correction are all derived from classical error correcting codes, which are extremely different in regard to the structure of the type of circuit. So it's not very friendly to integrate error correction into signal processing. So my passion is if we can come up with error correction that use quantum signal processing to perform error correction, then it becomes more friendly to integrate the two. Then we might have a better chance to use quantum signal processing to simulate large-scale system without having to wait for fault tolerance to arrive.
Yeah, so quantum helping quantum, right? One subfield helping the other, and the whole field as a whole. We have a question from Crowbar Massage. Is Google Quantum AI close to implementing signal processing in any applications?
What I showed is one case where we use quantum signal processing to increase accuracy of our quantum parameter learning by 1 magnitude. So I would call it a practical case. It's extremely useful.
Yes.
But hopefully there will be more. Hopefully there will be more such experiment in the future.
Maybe this is an invitation for the person asking the question to try and finding new applications, right?
Exactly. We
are gonna go with one last question. So, Shul0K asks, is the improvement specifically from characterizing the drift?
Yes. So what I haven't had time to go through is indeed in the drift. So as you see, like if a parameter is drifting, right, then it's very hard to say how accurate my learning is. If I'm comparing a method such our method, which can monitor the drift faster against another method which only give you an average, a time average of water, it's very hard to compare the two, right? Because our method will show some kind of parameter as a function of time, and then but definitely the fact we can monitor, we can see with our eye the parameters drifting is already an improvement. But unfortunately, I didn't have time to go into that detail. But yes, the answer is we were able to improve the accuracy of drift because, as I showed you, it is much shorter than the alternative circuit, so you can perform the repetition faster than the prior art to monitor the drift parameter. Good question.
Yeah, great questions, everyone. With this, we have concluded our talk and our questions. Thank you so much. Thank you so much for your presentation and your answers. And if you want later on to go to Discord and check out and everybody ask questions, everybody can answer each other's questions. Or Murphy, if you want to join our Discord, we can make sure you have the link and check out the different questions that everybody has. Also,
I will definitely try to join. Yeah.
Also, for people joining from a different time zone, that's a great place to ask questions.
Yes. Thank you so much, Catalina and QHack. It's such a fun event. I wish I can see all the participants.
Well, there's over 140 participants, and everybody stay. Don't go yet. We have a giveaway. So Murphy will say goodbye to you, but hopefully everybody will stay 2 more minutes so that they can get a chance to win a giveaway.
Good luck.
Thank you.